cell counters. So now I would invite Dr. Anil Handu to start his presentation. Thank you, sir.
Thank you, ma'am. Thank you, Dr. Sindura. And at the outset, I would like to thank Dr. Borges, Dr. Gujral, Center for Oncopathology, and my chairperson, Dr. Subramaniam, along with Dr. Sindura and Dr. Vatsala, to be there and giving me this opportunity to share my thoughts about quality assurance in hematology. Uh, it is indeed my privilege, in fact, to be talking when I'm being hosted by Dr. Sindura and Dr. Vatsala, who happen to be from my alma mater. At least they are currently in the same institution where I have learnt my pathology. So thank you, giving me this opportunity. I have no significant disclosures to make. Majority of the talk which is going to be discussed today is a lot of it either my personal experiences directly from in the laboratory or from the available literature. So what I have done today is I have just put in a preface because generally speaking, people do not really look at quality assurance talk, with a lot of enthusiasm. Most of us feel that it's a dull, mundane, and a boring topic. But I'll try and try my level best to make it as interesting as possible, keeping in mind that we need to also adhere to certain timings. Now I have put in some cases there. I'll be talking a little bit about how standardization and quality assurance is taken care of, some concepts with respect to terminologies that are used in quality assurance, a brief introduction, IQC, EQA, etc. All these terminologies which will come up, and finally some take summary and take home messages. So to start with, I'm just showing you this aeroplane, and I'm sure a lot of you might be thinking, why am I taking you onto a flight right at the inception of the meeting? The reason is a lot of us, in fact, most of us would have taken a flight at some point of time in life. And every time we've taken a flight, we've never been really scared, that we will not be landing or it'll actually meet with an accident, And the reason perhaps for that is that there is a significant amount of reliability and trust on the technology which is being used, on the people who are running it, and eventually people who are actually flying and getting us down to the final destination. So keeping this in mind and keeping this context in place, let's try and see how dangerous is healthcare today. So if you look at the encounters, a death encounter which you will have in episodes like nuclear power accidents or European railroad accidents, it's about one death per 100,000 encounters. When you move on to driving and chemical manufacturing, it's about one death in about 100,000 to more than 1,000. And just look at the statistics now. You have more than one death per 1,000 encounters in bungee jumping, mountain climbing, and mind you, healthcare as well. So healthcare can be a pretty dangerous game, and therefore one needs to be extremely cautious. Now let's see what are the different types of errors which happen in healthcare. As we would have expected, more than half of the adverse events occur because of some surgical procedure that has been done and something gone wrong during the surgery. Next come complications of drug therapy and therapeutic mishaps. But remember, diagnostic errors are one of the commonest errors which happen in non-operative events in patients. So therefore, we are into a very, very difficult and a very murky business. I'm sure most of you would again be wondering, why am I showing you this lady's picture? And I'm not sure, this is not a part of the quiz, by the way, but I'm sure you know who she is. She is Angelina Jolie, and I know most of you, at least the boys, would have identified her very clearly. And I'm also sure a lot of women would also have picked her up very quickly. You know why she was in the news? She was in the news because she decided to go ahead and do a mastectomy based on one hematological molecular investigation, and that was a BRCA gene test. Now imagine a lady deciding to undergo bilateral mastectomy as well as undergoing oophorectomies just basis a single test. Imagine the kind of pressure that the laboratory would be under to ensure that the test which is given out is of the best and the highest quality on which the decision for this patient, for this person would have been taken. So giving this backdrop to everyone here, please look at this. You have nearly 70% of medical decisions being taken based on a laboratory test today. So isn't it extremely important for us to ensure that the test that is done is of the best possible quality and is giving the most accurate and precise results to the patient? Of course. Now, I know a lot of us are who have joined today would be from the medical colleges and the postgraduates who are pursuing their courses. And invariably, I don't know how many of you really have gone through the quality assurance as a topic, in your routine practices. But as far as my encounter was concerned, for me, this was nothing but an exam question, which was a major question, supposed to be a major question in the exam. And for that, I had prepared. Of course, it never turned up, and I'm gladly, been through that, and I'm happy that it didn't turn up as a question, because I really did not understand at that moment as to what this quality assurance really means. And then I had my first practical encounter. This was in 2004 when I had joined a hospital laboratory, and they were trying to undergo what is called the NABL accreditation, and we'll talk about it a little bit later. And there was this internal audit which happened, and the auditor came in and started asking questions to a lot of people. And he also came to my room and said, as a part of the process, I need to ask you a question. And I said, fine, what's the question? He says, how do you do a particular test? And I said, look, this is how I do it. He says, how do you know this process, that this is how it is to be done? I said, well, it's given in DAISY. He says, do you have an SOP for it? You know what my answer was? I said, what is an SOP? So SOP, I did not know what SOP stood for. And SOP, eventually he told me, is a standard operating procedure. And that's how my journey for quality assurance started. Now, during that same assessment and same process, our technologist was summoned in the final NABL assessment, and he was asked, why do you run quality control material? And do you know what the answer was? He said, it's for NABL. And if you ask anybody in general and ask them what is all what do you how do you actually do quality, all they will say, it's a lot and lots and lots of paperwork. So therefore, it is a big challenge when people are actually trying to do quality assurance. And imagine I'm going to be taking a talk for all of you, with that kind of a background that I'm telling you as how people really look at it. Nevertheless, let's see a few cases to understand why it is extremely important for us to have quality assurance in the laboratory at the first instance, and then how we would want to take it further in our life. I'll give you, and these are real life case scenarios which have happened with me at some point of time in my lifetime during my last 15 to 17 years of practice. So this was a patient who was about 67, 68-year-old lady. And my boss actually walked into my room and said, showed me these two results, and said, this lady has gotten this test done on 1st of July in 2017. And then on 3rd of July, she's gotten these tests done again. And, I am not able to figure out which report is right, because if you look at the CVC part of it, both the CVCs are comparable, as you can see over here. But the moment you go down and look at the iron profile of this patient, the iron profile on the left hand side is very characteristic of an iron deficiency anemia. That's on the first. However, when you go on the 3rd of July, just look at the iron profile. I mean, it just does not seem to be the same patient. Now, the simplest answer, and when my boss asked me this question, what would I answer? My simple answer was, because he didn't tell me that which was the laboratory where it was done. So I said, look, I think one of the lab reports is wrong. He says, I said, where did you get it done? He says, from your lab. I said, then both the reports are correct. Now tell me, who is the patient? The patient was his mother. Fortunately, I was aware of the fact that his mother was a chronic renal failure patient and she was on dialysis. And on the first, that was a pre-dialysis report. And on third, it was a post-dialysis report. And in both the cases, fortunately, she had maintained her hemoglobin, but her iron profile had changed completely. And that's a normal thing to happen. Now, again, it becomes extremely important to have the information about a patient. Another case, a 32-year-old female who had relapsed acute myeloid leukemia for stem cell transplant, and she was stable. Her stem cell enumeration was sent to the laboratory. And just imagine the dose was just zero point zero 0.02 kilograms per body weight. You need more than two to go ahead with the process of, transplantation. And especially in allo transplants, the dose is slightly higher. Also, the dose required is slightly higher as well. Now, a repeat sample was sought, and the results now came as 11.3 per kilogram body weight. So obviously, there was something wrong with the sample that had been sent in the first instance. Third case, this was a 55-year-old male who had come to the hospital for a routine follow-up post valve replacement therapy. He was on anticoagulant acetrom, which is like the vitamin K antagonist, about at 4 milligrams per day, and he was just getting a regular PT INR monitoring done. He would normally get it done from a laboratory which was near his home, but this time he decided no, he will get it done from our own, from our hospital laboratory. When he sent us a sample and we took the sample apparently properly, what we got was a very high prothrombin time. In fact, the sample never showed any coagulation. So the patient was kind of, really worried, and he said, doctor, can I just get my same sample and I'll get it tested from my own laboratory, because I have not done anything with myself. I have not changed any medication. I have not taken any food stuff or anything which is going to be explaining this whole thing, because he seemed to be a very well informed patient with respect to his disease. So, I thought just let's give it, because in a sector where we work, it's generally not advisable for us not to, be with the patient. So we went ahead and decided, okay, fine, take the sample. He took the sample and I only requested him, sir, please make sure that when you get your results, can you just share it with me? He says, fine. When he shared the results with me, he got a result which was absolutely well within the therapeutic interval for what he needed. Obviously, there was something wrong with us. We realized that, a little later when we investigated, because it became a big query for us, we realized that sometimes you need to do what is called reassignment of ISI for the prothrombin reagent when you're using it in your laboratory, because sometimes the lot may not be giving you the right ISI for that particular patient. I'll not delve into it in details, but when we eventually did the activity, we realized that yes, we were able to sort it out. Now, another case scenario where we had a patient, visiting India from Africa for a bone marrow transplant. He was a sickle cell disease who was having multiple, crises of sickle cell disease. His peripheral blood film obviously is showing very characteristic sickle cells, and the hemoglobin HPLC is also showing a characteristic scattergram or scatter plot of a sickle cell disease. Now, what could go wrong in this? The thing is that many a times the sickle cell hemoglobin, when it is eluting in this particular window, we need to confirm it by doing some alternate tests. Though we had sickle cells here, so we were pretty sure, but we still do what is called a sickling test as a part of our routine examination process. Now just look at this, what happened. This is how the sickle cell should look like when you are actually doing this test, the sodium metabisulfite test. You will find these sickle cells under the phase contrast microscope. But what happened in this particular patient is, in the case, we did not get any sickling at all. And this was absolutely, difficult for us to understand. So we tried doing a lot of activity. We took help of one of our laboratories nearby from one of the nearby hospitals. They helped us and they did a sickling test and they showed that the sickling was positive. So we went ahead and reconstituted, got the fresh reagents and got fresh reagent preparation done, and eventually did a test, and this is what we saw. We got sickle cells there as well. So obviously what was happening in this particular case was there was a patient who was actually a sickle. We knew it should be a sickle, but our reagents were not functioning properly. And the reagents had actually been with us for almost 3-4 years, because normally this test does not happen, so in such large proportions that you need to keep on doing, preparing, getting fresh reagents all the time. So somehow these reagents had lost their potency and we were needed to get fresh reagents. So again, something which was happening analytically in a laboratory. Another case wherein a 4-year-old male child, a known case of precursor B cell ALL, after induction therapy, when you treat the precursor B ALL patients, you give induction therapy. Nowadays, it's a norm to do what is called minimal or measurable residual disease. We reported it as MRD negative. Everything seemed to be okay, except that the patient relapsed just about a week, 3 weeks to 4 weeks later. We reevaluated the entire case and we realized there was something wrong with the sample itself and, of course, even in the interpretation. The other case was that there was a 54-year-old female, who was diagnosed with generalized lymphadenopathy. Peripheral blood did not show a significant abnormality, except that bone marrow was showing lymphoid infiltrates. A flow was done, which was called as CLL. Eventually, the molecular studies were done for translocation 1114, which came out to be positive. A review of the flow cytometry was done. It turned out to be a mantle cell lymphoma. Obviously, interpretation was in question. Now, when you see all these cases, what were the various issues which happened? If you look at the first two cases, you had a problem with the sample. In the next two cases, you had problem with the way you were doing the test in the laboratory. In the last two cases, it was the interpretation which was at fault. So issue with the sample, issue with the technique, or issue with the analysis and interpretation. So obviously what is very, very important is not only to do everything correct, it's the right thing with the right time at the right patient in the right way, getting you the right results. And for all that, you need what is called training, experience, and application. Now, why do we need to keep all this in mind is because behind every sample that you get in a laboratory, there is a patient. And what if you are in the tube someday? So you must remember that we need to do everything right. So what makes you do everything right? The only way to do everything right is by ensuring that you're doing something which is called quality work. So when you go into laboratory testing in general, there is a huge wish list for everybody. You know, what are the various wishes that everyone has? The patient is actually very quickly wanting to get the results done because and at the reasonable cost and as quickly and as reliably as possible. The clinician wants the same. And do you think we are any different? Sorry, we're not. We do the same as well. We also want the reports to be given appropriately and making sure that we have an appropriate quality management system available in our laboratory. So what is the wish list therefore for the patient, for the clinician, or for the laboratory physician is to get a rapid, a reliable, and a cost-effective test for the patient so that they are able to take appropriate action for patient care. So if you look at it from the perspective of the patient, the clinician, and the lab physician, it's always a patient-centric approach with respect to any testing that's done in a laboratory. And therefore, the concept of quality comes into the picture. So why do we talk about quality management system? We talk about quality management system because it is ultimately something which is absolutely patient centric. How is it patient centric? It is patient centric because there is a patient who has come to the laboratory or has chosen to get the samples picked up from the laboratory. This sample has to eventually travel in an appropriate manner to reach the laboratory. In the laboratory, the person has to actually identify whether the sample has been, received in an appropriate manner in which it would not be jeopardized in some way or the other. The accessioning should be appropriate so we do not mix up any samples with anybody else. And once we have accessed, we may eventually need to even transport it to a farther location for doing some esoteric tests and then ensure that when you're doing the test in the laboratory, you are ensuring that the quality of the test is maintained. In other words, a test, you should get a positive test as a positive and a negative test as a negative, and it should not be just as a just as an activity which is not really concerned about a patient. And finally, once you have done everything, it should eventually be able to reach back the patient in such a way that you are able to give everything properly to the patient. He should get the right result for him to take any action if it is needed. When this entire circle of activity is happening, you need all this to be managed at the parallel end. For instance, for not only for the data and the laboratory management, you also need to ensure that whatever is needed at whatever point, the supplies are appropriate, they are of appropriate quality, because only when you get material of appropriate quality will you be able to give the correct result to the patient. So if you look at the laboratory now in the backdrop that I have given you, I guess you would be now comfortable in assuming that yes, I need to provide a quality service to my patient. And how will you do that? You will ensure that you are able to give an accurate test, a precise test, a cost effective test, and all this should be done in a reasonable time frame. In addition to all this, we should also be able to provide opportunities for training and career growth, which most of our postgraduates are actually going on doing at the moment. And of course, you should be able to do it in a safe and a secure environment. And there should also be a possibility of innovation and research. Now, when you look at quality assurance, there are lots of times when you ask anybody, the moment you will come out and become a party to any of the laboratories where you will be functioning, quality assurance to a lot of people, as I told you previously, is something for NABL, right? But in reality, is it really for NABL? That's what you should do. The answer to that is not really so, because it's not only paperwork, it's not only the development and retention of quality control charts, it's not only to choose the correct methods, it's not only through proper education of personnel or appropriate handling of specimens or correct reporting of results. It is actually an activity which is supposed to make sure that all the results which are emanating from the laboratory are correct to the patient and the lab is functioning appropriately and satisfactorily to provide the results in the reasonable time frame. So when we look at quality assurance, the objective of quality assurance is pretty simple. It's intended to ensure that there is reliability of the laboratory test report. And I cannot overemphasize it because I've already during my prelude given you the preface, given you the enough evidences to suggest why we need to have quality assurance in our laboratory. Now, how do we ensure that there is quality assurance which is appropriate in our laboratory? I had some time back, I had visited Pittsburgh, and just look at this. This is the socket which was there in which I could have pushed in my charger plug points. Is it possible for me to put it here? No way. Now I need to do something to ensure that I am able to put this plug into this socket. So therefore I had this adapter which was available with me, and I could actually use the adapter, ensure that with that adapter I am able to go and put this charger into that point so that I'm able to charge my phone. Now when I look at this, do you know how many different types of sockets are available in the world? It was such a revelation to me when I actually sat down and started looking at standardization. Sockets itself, there are so many different types of sockets across the globe just to put a plug inside. And imagine if you're not carrying the right plug to be put in the right socket, what will happen? And just for your information, for your general information, the number of sockets which are available in the world are from A to O, and in different countries they're different. But the usual countries which most of us visit most of the times are these, and these are the different types of sockets which you have. India, you have these three types of sockets which are available. Just look at these three sockets. Are you able to actually see any of them over here? None. So therefore, standardization becomes extremely important. How do we standardize? Especially the laboratory part of it. We have standardized the laboratory part of it by adopting a standard called ISO 15189. That is International Organization for Standardization Standard, and the standard number is ISO 15189. Now, whenever we talk about the standard, we are talking, this standard is an international standard. It is not a standard which is local, and the standard has been locally adopted by NABL. So this is the accrediting body which is actually giving us the possibility of standardizing our techniques to this particular standard, and then they accredit our laboratory against the standard whether we are complying with the requirements of the standard. So the NABL stands for National Accreditation Board for Testing and Calibration Laboratories. Now, when we do quality assurance, and I'm sure all of you know about this, there are actually three major components of laboratory testing. The first phase is where you are actually procuring the sample from outside, from the patient, and getting it into the laboratory testing area. Now, that phase is called the pre-analytical phase. That means the analysis is yet to happen. The second part of it is the analytical phase where you're actually testing the sample. And finally, once you have analyzed the sample, now you go into the phase where you're actually making sure that the results are given out to the patient. And if you need to store the samples or do anything else or clean up the area, that's called the post-analytical phase. So this is the usual process flow. A specimen is collected, it is transported, test request is recorded. In the analytical phase, you analyze only after ensuring that you've chosen the right method, you've chosen the right instrument with an appropriate calibration in the check. You process the sample, do a data processing, get your records, and finally report it to the patient. There are a lot of terminologies which we must know and remember. Now, what are these terminologies? A lot of these terminologies are actually used interchangeably by a lot of people. For example, quality assurance, quality control, quality management, they seem to be such terms that almost everyone uses them interchangeably. Unfortunately, they really are not the same. There is a huge difference between all of them. While quality assurance covers a lot of gamut, the quality management is a bigger umbrella under which the quality assurance and quality control come. And quality control ideally is a term which is restricted only to what is called the internal quality control. And we'll talk about a little bit later. In addition to that, we also have the external quality assurance or the proficiency testing or intercom laboratory comparisons, accuracy, precision, reproducibility, certification, and accreditation, which we will touch upon a little bit in our subsequent slides. Now, the first point that I want to tell you is about precision. Now, when we talk about precision, it refers to what is called the reproducibility of the result. If you look at this cartoon, which I just showed you, you saw all the results going into one area, right? When they all go into the one area, they are actually precise because they are all falling in the same single area. Every time you run the sample, it's coming to the same specific area. But is it falling right in the center in this bullseye? No, it's not. So while it is actually fitting precisely, it is not accurate because it's not going onto this green area in the in what is called the bullseye. Now, what is possible to do for precision is to ensure that we might need to do what is called calibration. We'll come to that a little bit later. Let's now look at accuracy. When we talk about accuracy, we're talking about all these values coming in and actually going to the true value or the value which we had defined for that particular analyte. So every time these values fall in the same place all the time, we're actually talking about something which is accurate. So you can remember, you need to be precise because you can never have accuracy without precision. Now imagine if the same dots which we saw previously here, they were all falling in one place. And eventually when we went to this particular area, they again all went to the same place, but this time they went on to the bullseye. So therefore, you cannot have accuracy without precision, but you can have precision without accuracy. And that's where the concepts of calibration and external and proficiency testing come into play. Now, if you look at this particular picture, you see all these red dots. What is happening? They are all falling all over the place. So in this case, neither are they falling in the green area. That means they are neither accurate, and nor are they falling together in one particular area on this particular bullseye. So therefore, they are neither precise nor accurate. And this is what we do not want in any laboratory with respect to the material when it is run as a control. Now, how do you ensure accuracy? So if you look at any laboratory, when we are trying to ensure accuracy, we do what is called calibration. Now, what do we mean by calibration? We have a material which has a defined value, which is otherwise called a certified reference material. Now, this is a material which has a known value. For example, if we say that we have hemoglobin, which is say 10 grams in a particular patient, this hemoglobin 10 gram in a particular patient will remain, accurate in that particular sample. Now we run this sample as a material which is going to be going into the machine. Every time it should give me the same value of 10 or a value which is nearby 10. That means my particular machine is actually showing me an accurate value of calibration. So if we do a calibration of a hematology analyzer, we do it for ensuring that there is instrument accuracy. So when I run a sample in my hematology analyzer and it gives me a value of 14 grams, and I then run the same sample, say for instance in any of your laboratories, and it gives me a 14 gram value, that means both our instruments are falling on the same calibration that we had. So therefore, a calibrator is a material which is a certified reference material, has got a defined value from somewhere which is being used, and it is supposed to get us that accurate value which it had. But mind you, do you always get the same value when you run the sample into a machine? No, you will not, because there will be differences in the environment, differences in the way the machine is run, differences between the temperature, the humidity, etc. So therefore, the value may not be exactly the true value of that particular material which you had used. Now, whenever you have a value, say for instance, you had a value of 14 grams, which was defined, and you got 13.8, but now you have to adjust it to the value of 14, then that means you're going to be adding to it zero point 0.2. This zero point 0.2 is nothing but a calibration factor. This is the simplest way I can explain it to you. I don't want to get into a lot of quality jargons because then you will not really be able to figure out what I'm trying to say. So calibration factors become important, which helps you to ensure that you get the target value that had been defined. So when somebody asks you what is a calibrator, calibrator is a material which has got a reference, which has got a traceability, and it has got a value which is defined, or a target value. You don't have a range for a calibrator, even though a lot of companies come to you and they tell you that a calibrator has a range. Calibrator may have a range, but actually calibrator should have only a target value. So remember, that's one very important thing. The second important thing is carryover. When you run samples in an instrument, the previous sample has to be washed away and only the next sample has to get in. So there are times when the previous sample does get washed away, but some part of it remains behind. Now that previous sample, imagine it had blasts and the next sample did not. What will happen? You will have blasts coming in from a sample which was there to the sample which never had. For example, a similar thing can happen in hemoglobinopathies. For example, you run a sample of sickle hemoglobin, and then immediately after you run a normal sample, there might be sometimes if the carryover is too much, the sample which is retained within the machine can actually be transmitted to the next one, and that's what is called the carryover. So we do not want the carryover to be there, and that's again extremely important for us to take care of, because otherwise we'll give wrong results. So I have a question here. The question is for a complete blood count that you do on a hematology analyzer, and I don't expect you guys to give me an answer right away. You can give us the answer in the chat box, and I have not given any multiple choices in this. I'm asking a direct question wherein I am asking, do we have a calibrator for any of the parameters of complete blood count? And this is the question which I would like all of you to think and answer, and we will talk about it at the end of the talk. Now, when we talk about calibration in general, we need to have a lot of checks in place. We need to ensure that we have the instrument which has been installed, and there's a thing called an IQ, OQ, and PQ. These are again quality jargons. IQ stands for installation quotient, which means that you are installing the machine in the laboratory. The second is the performance quotient, wherein you're actually trying to assess whether the claimed stuff from the instrument company is actually being done by the instrument or not. And the third one is the operational one. So in all of these cases, you're basically trying to see whether the operations, the installation, and the performance of the machine is coming out in an appropriate manner. So you also run what is called a calibrator to set your values in the machine. For example, you might want to run a calibrator for, say, for instance, a prothrombin time, etc. So in such cases, you will put the calibrator first, get your appropriate values, and then do what is called the precision checks, the carryover checks. And importantly, in a hematology analyzer, you have two modes of running the sample. One wherein you put the sample in a cassette and the cassette moves into the machine, and the other one wherein actually you open the lid of the tube and you push it into the machine, which has got a probe, and that sucks up the sample. These are called closed and open modes, and calibration should also be done on all of them. And once you have done the calibration, because calibration invariably is done in what is called the operator mode, or the administrator mode. You would have understood the administrator mode more, because that's what happens in IT systems in majority of the places nowadays. So the administrator mode should also apply to the patient mode, and that's where you have to run your calibrator as a sample and get the values, and then you also run the various levels of controls. Coming to internal quality control in hematology practice, uh, what do? You basically, when you're running internal quality control, you're actually checking for precision. That's your aim. You're trying to see, when you're running a sample, is it able to give you the same value again and again and again? Because again, as I told you, a control is a sample which has a range. A calibrator has a target value. So when you use a calibrator is for accuracy. When you use a control, you use it for assessing the variability, the day-to-day variability which the machine can have. So invariably, to check for precision, you will run it at least 10 times, and you will check the variation between the two. So what is a control? What material is the control made of? Again, I would like you guys to, think about it or get to know about it. And this is more of a question, and we would like to answer this at the end of the talk. Now, whenever we run controls, you ran the control into an instrument which had certain defined values, or ranges, and you were expected to get those values, from the instrument, and then you were supposed to interpret them. So, how did you decide you will interpret them the way you are interpreting them in today's day and time? The attribute to this goes to this person by name Walter A. Shewart, because he was the first person to give us the charts. And this guy, used to work at the Bell Telephone Laboratories. He applied these statistical based control charts to interpret industrial manufacturing processes. And eventually, it was also improved upon in 1950s by Levy and Jennings. And that's what we use nowadays, the Levy-Jennings charts. And of course, we all know James Westcott, who has given us the rules to interpret these Levy-Jennings charts. And again, without getting into significant details of how exactly to interpret these Levy-Jennings charts, there are these multiple rules which are looked into. And when we are looking at these rules, all these rules are interpreted not in isolation. So you do not only run one QC sample and then see the violation. You run all the QC samples together, and then you look at multiple rules together, and then only you interpret them. So there are these multiple rules. I'll not get into details of this, only for the simple fact that because if I get into it again, you might not want to really know more about it. Having said that, there are certain rules which a lot of people have started believing that they don't want to use in hematology. For example, the 10x rule. That means all the values of the controls are falling on one side of mean. And I'll talk about mean and standard deviation in my subsequent slides. There is also a rule called 8x rule, and of course some modified rules like 12x and the 7t rules. I'll not get into detail of that. I will talk about it a little later. So when you run a sample which has got a defined range, you are expected to get that sample's value in that particular range. So if it does not come in that particular range, that means it has gone what is called out of range or out of control. Now, when it goes out of control, you have to define what do you mean by the term out of control. Is it what is called a warning rule, or is it what is called a rejection rule? So when we say it's a warning rule, that means the value has gone off beyond what we were expecting it to go, but it has not reached a stage where my machine is giving me inconsistent or wrong results. So that time it'll only be a warning rule. But if you have reached a stage where it has gone completely out of control, where you were not expecting it to be there at all, then you would call it, then you will need to stop the testing, identify the problem, and even repeat the patient samples and controls to get the right results. And it's important because you don't want to give wrong results to your patient. So now let's look at a little bit about statistics which are involved in identifying and defining the controls when we run it across the any of the hematology analyzers that we use. We have, and I'm sure most of us would have read this in our mathematics right from the standard 8. This is taught the normal distribution curve. And in the normal distribution curve, the middle point which you see here is what is called the mean. And then anything plus or minus 1, 2, and 3 standard deviations is what is looked at. So what is in within one on either sides is the single standard deviation, a deviation from the mean, and then you have the variability across this entire spectrum, which is called the coefficient of variation. I'll talk a little bit more about this in my subsequent slides. Now let's see, we ran a sample of blood into the machine and we looked at the RBC values. We ran it 10 times. So these were the different values we got in millions. That's 4.58 million, 4.55 million, etc., etc., etc. Now in this case, what is the mean? We will add all of these values just as the way we have done over here, and we divide it by the total number of values which we took. They were 10. And what do we get? We get 45.46 divided by 10, and the mean is 4.55. So that was our mean. Now to find the simple mean, we have the sum of the values which was there divided by the number of the samples. Seems to be. Sorry, I think this is stuck.
Oh,
Sir, you can exit the full slideshow mode and then again switch back, sir. It sometimes moves.
I'm trying to do that. Just give me a second. Your laptop, please. बोलना यार. Are you able to hear me?
Yeah, we are able to hear you.
I'm so
Uh,
sorry. I'm
no,
so sorry.
Anil, if it'll take you a couple of minutes, then I have few slides. I will just take over a little bit just to summarize things.
I think it's almost done. So I'm
Yeah.
just sharing it again, okay?
Okay. Yeah. Yeah. Your slide is visible, but it's not on the PowerPoint show.
Yeah, I'm trying to get it to the PowerPoint now. Okay, I think by the time, all right.
Yeah. It's done.
All right. So I'm really sorry for this. I don't know why it got stuck, but never mind. So the idea was to basically give an idea about how the mean is calculated. So you had the values which I just showed you. All the values are taken as a sum, and the total is divided by the number of the variables which we had taken. And this is the standard deviation. The standard deviation is represented in the form of sigma, and that's like the number of values minus the mean to the sum of and to the square of that divided by n minus 1. And to calculate the coefficient of variation, we have the standard deviation divided by the mean, and that's how the mean and the standard deviation is taken. And this is something which I was showing you earlier. So this is the mean which we had calculated. This is the mean, the number minus the mean that we got, the value minus the mean, and the square root or square of that. And eventually, this is the sum of that square. And eventually, when we calculated the standard deviation, this is how the standard deviation and the CV has been calculated, right? So I hope you have understood the concept of measurement of the standard deviation. I'm sorry, I'm just trying to place it such a way so that you're able to see, right? So that's how the mean and the standard deviation is calculated. Now, this is something which I had planned to give you as an exercise. I don't know whether you are able to see it, but we can share it with you later just to see the CV, what you're getting for this hemoglobin values, which I'm mentioning over here so that you're able to understand the concept. Now, remember, when we talk about quality control material, we need to have a material which is similar to what we have as a blood sample. So what will be similar to a blood sample? It will be only blood. So for all practical purposes, the material that is used for a quality control material, and asked this question previously, is the material which is same as the human blood. It is a stabilized human blood which is used, and this is used for everyday quality control. So before you run the patient sample, how do you know that your machine is giving you the right value? Or before you run any manual test also, how do you know that your manual test is actually giving the right results? You will run what is called a control along with it. So there has to be a positive and a negative control when you're doing a qualitative test for a positive and a negative. Whereas when you're doing a test which has got value, for example, a CBC, you will need to have a material which is going to give you quantitative results. So therefore, the material that is used is the QC material. And as I told you previously, we talk about what is called the Levy-Jennings chart. So if you look at this Levy-Jennings chart, which has been plotted for the hemoglobin, you're able to see that the values are coming on all the sides of the mean, which is this line over here in the center. And I have deliberately put this blue dot over here just to show you what do you mean by something which is out of control. So something, when the moment you have anything which is out of control, you would obviously want to stop the patient testing. So your QC values are expected to be within the 2 standard deviations, and anything which is going beyond the 3 standard deviation is supposed to be out of control. Now, what are the various IQC materials which are available for hematology analyzers in general? You can have commercial controls, you can have a retained sample which you can use, and you can also use what is called the moving averages or Bull's algorithm. I'll get into a little bit detail of most of them, but remember, when we talk about commercial control, the usual question which a lot of people keep asking is, what level of control should I use? Should I use a low level control or a mid level or a normal level control or a high level control? Now it depends upon what is the therapeutic implication of that particular test. For example, if there is a test wherein a high value beyond a certain level determines that there will be a therapeutic decision, then you will definitely use a high value for sure. If there is a test where a low value determines what it is going to be done for that particular patient, then you should use a low value for that test. However, if there is a test where there is an entire spectrum, then you should use all the levels. Usually in CBC, the preferred methodology is to use the low level, the intermediate, the normal level, as well as the high level. Now, when we use the controls in a hematology analyzer, the biggest challenge which a lot of people face is that this is a commercial control. The one which is available is, after all, stabilized human blood, and this stabilized human blood, does not remain stable for more than a specified period of time. There was a point in time when the open vial stability, the moment you open the vial, would not be more than 7 days. However, fortunately for this, a lot of companies have come out with significant stability values, and over a period of time, the stability has gone beyond 15 days also in some commercial controls. Nevertheless, the open vial stability, which is defined by the vendor, is what needs to be taken into account. And after that, the sample will anyways deteriorate. So the challenge is, how do you establish your mean and standardization? So when you want to do the mean and the standardization value of this particular case, then you will run the controls in parallel. For example, if you follow CLSI guidelines, it says that you need to run the new controls along with the previous controls for at least, if not more, 20 runs, so that you are able to get the values wherein you can have an overlapping thing and you are able to establish your laboratory's mean and then compare it with the two standard deviations. Coming to internal control that we use in our center in my laboratory, of course, we use the control charts, we use delta check, we use consistency, and the concept of delta check is something which I would like to emphasize upon, especially to our postgraduate students, is because there are patients, who would be in your laboratory, in your hospital for a long time, and they would always be getting certain values. If there is a huge change between the previous and the new value, then you obviously want to figure out what has gone wrong. So that's also a delta check which people keep into account. Fortunately, nowadays, majority of the analyzers will have the mechanism of recording all the data on the analyzer itself. For example, this is from one of our Coulter analyzers, wherein you are able to see these yellow dots over here identified on the analyzer itself. This is from another analyzer which we have, the XE2100 in our laboratory, and of course the Mindray instrument which we use currently. In all of these instruments, you have these various parameters which you are using, and these parameters are actually able to give you the values which determine whether you are doing the right job or not. Other than that, what other things can be done for the internal quality control? You can run the samples, between different analyzers. There are laboratories where they have more than different two vendors, who are having the machines, and in both of these machines, you can run the samples. You can also do lot validation after sample change, and of course, you can correlate with the patient samples. So a quiz which I again want to give across to all the postgraduates here is, what is the source of quality control material which is used on hemostasis analyzers? Hemostasis is again a part of hematology, and of course a lot of laboratories have it in chemistry also. But what is the quality control material that is used on hemostasis analyzers? There is also a concept of using retained samples. You can have a previous sample, and this is important because many a times your QC material might just finish and you're not able to get a fresh QC sample from the vendor, and in such circumstances you might need to actually run previous days run sample or in the morning run samples, and therefore you need to define how will you consider something which is actually doing the right thing. Now, coming finally to the proficiency testing, why do we do proficiency testing? Now, proficiency testing is nothing but a challenge sample. Herein, the sample actually is coming from a third party invariably, and in this sample you have a defined value just like a calibrator, and the idea of doing a proficiency testing is to ensure that you're testing accuracy also to an extent. So proficiency testing is a again, as I told you, the sample involves participation either in a nationally available program or an international proficiency testing program. And in this case, when the sample comes in into the laboratory, it is to be tested just like any other sample, so that you don't have any biases as to treat it in a very different manner. And the results are sent across to the proficiency testing program provider, who eventually evaluates your test results and identifies it as a deviation index from where there has been a peer group. If you have 10 machines of the same type, you are actually able to analyze whether the data which is coming from all the 10 is comparable. Now, this also involves in case when you're not able to get the right results from the PT provider, you will need to go back and identify what is wrong with your machine. E- EQA also helps you to actually define the biases which can happen in a particular case. These are the various types of PT provide, reports which come. This is from the RCPA survey, which is also used by some people. Again, when you do not have a PT program available, you will still do what is called split sample or a blind sample testing and identify the ways and means for identifying if the quality control is appropriate or not. So what are you trying to do? You are basically trying to identify any problem which can happen to the patient's sample, because you don't want to give the wrong results for the patient's care. Ultimately, it's the patient's safety which is extremely important. There is also a concept of what is called total quality assurance. Total quality assurance is when you involve the internal quality and the external quality assurance together to ensure that the results emanating from your laboratory are near perfect or best for patient care. So what do we achieve when we do all this? Why are we actually talking so much about quality assurance, so much about jargons in quality, etc.? What do we achieve by doing all this? We are actually standardizing all the functions, and I showed you the picture of standardization, by taking the example of the socket and the plug. We are doing what is called the monitoring in the laboratory to ensure that the results that you are giving out to the patient are correct to the patient. We are identifying and ensuring that the problems are corrected if at all they are there. And of course, if you're going ahead with the accreditation part of it, we are also being accepted by the accrediting body. In India, it happens to be NABL, so by NABL. And most importantly, within the staff and the doctors who work in that laboratory, we develop what is called a quality culture to ensure that the results emanating from our center are in the best interest of the patient care. So to summarize, quality is not an enigma. You have the stages in a laboratory of pre-analytical, analytical, and post-analytical stages. And if you look at any good laboratory practice, the laboratory test results are actually correlating or corroborating to a clinical diagnosis eventually. And this is actually having a huge implication in patient management. I would like to thank all of you for your kind attention, and this is our team. And I would like to put my acknowledgements on board for all the people who helped me at some point of time in my career. Thank you very much, and I am happy to answer questions if there are any.
Thank you, sir. Sir, Dr. Mani sir, you have comments, sir, on the talk, and you wanted to share your PowerPoint here, sir.
Yeah, yeah. I just wanted to say that this is a important topic to be understood by the postgraduate students, because it is what they will be required to do most of the time in their career. And on the other hand, a 1 hour talk on this is, if you ask me, very short and can only be a brief introduction. So to a certain extent, I just was going to summarize some of the what Anil was saying into a brief summary of sort. This is not pedagogical, but this is what it should be the final take-home message, which should be there. So assuring quality assurance, because many students, when we ask questions, they get confused between what is quality assurance and what is quality control. Quality assurance is actually the huge portion of everything about a lab. So anything that you do in the quality to assure or to improve the quality in the lab of all processes, some total will come as quality assurance. Generally, quality management system is part of the quality assurance. So the quality assurance will be, and generally the quality assurance is patient centered, and it is what is going to be the utility for the patient is the most important part of the quality assurance, rather than statistics and measurements center. So quality assurance includes quality control. It subsumes quality control under it, but it is the overall arching thing. So The second thing is just to basically cut through the jargon as well as try to simplify. I've tried to simplify this. I'm not saying this is the most accurate way of doing it, but it is like one slide which will be there. So for any test, you have to do quality control. So this, what I've said, is for a quantitative test. So in a quantitative test, you calibrate if there's a calibrator available. So what is the point of calibration? It reduces the inaccuracy. So in certain parameters in hematology, like D-dimer doesn't have a calibrator. So each company, various companies produce various kits, and the various kits give you various measurements. So there is going to be, you have to understand this, there is going to be a lab to lab variation in the value of D-dimer everywhere, because there is no internationally accepted calibrator for that. So calibrate is to measure, is to reduce bias or inaccuracy. After you have done the calibration, run the controls to measure your imprecision, as well as to say what is the range of variation of values you can have for a stable control. So monitor the controls to ensure stable measurement of uncertainty. If the control is having huge range of uncertainty, now the problem comes between the standard deviation and a coefficient of variation. So coefficient of variation is used to compare between which tests, which parameters are more or less imprecise between. Say, for example, if I take a CBC parameter, a hemoglobin will have a 2% coefficient of variation, whereas a platelet count will have a up to 9-10% coefficient of variation. So a platelet count has more variability than a hemoglobin. So a hemoglobin between two labs shouldn't be varying much if they are calibrated and in control. So that is the message to take out of a coefficient of variation. So a standard deviation is what is used for your quality control regularly. If the control is out, then you have to see what has happened to the analyzer, recalibrate if required, and verify again the measurement of uncertainty. Most important thing is always a good quality practice or a quality goal is always keep looking for ways to reduce the uncertainty in your measurement. One of the jobs of a proficiency testing or a external quality assurance is also to evaluate accuracy. So as Anil Handu has already said, so this is a 4-sentence summary which I would like the students at least to take home. So now the tests can be quantitative or qualitative, or a qualitative based on a quantitative variable. So qualitative based on a quantitative variable, for example, in myeloperoxidase, we say positive or negative. It doesn't have a number, it's a value. But the positive negative is based on a 3% cutoff. So you're having something quantitative, which you are converting into a qualitative. So wherever you are using a cutoff based, your control should be very close to the cutoff. Whereas a purely qualitative, you might have to look for agreements. So many things. So whenever you think of a process, you have to think in terms of what you can measure out of the process when you are thinking in terms of quality. So for many qualitative indicators, and internal quality control, especially within slides for an MPO, is important. So if the neutrophil is not showing in the myeloperoxidase, which it should be showing in a slide, then you should not give a negative in order to reduce the false negativity. So these are, so any test you think of for the residents, just don't think in terms of principles and how the test is done. Also think in terms of what is the quality control procedure for the test, and how will you know whether the test has worked or not for every test which you learn of. That's all I have to say. I think.
Thank you, sir. Now I'll direct some questions in the chat box to both Dr. Anil sir and Mani sir. The question was to explain the measurement of uncertainty in detail. Sir, Anil sir, could you please take up this question?
Okay, so if we talk about measurement of uncertainty, now I did touch upon it a little bit, wherein I said that when you run a sample of, say, a control which has got a defined value, how sure are we that every time we run the sample, say for instance for hemoglobin, we decided that the range of that particular control is say 12 to 14 grams. Now I expect the result to come between 12 to 14 grams. How sure am I that I will always get it between that particular interval? More importantly, the point is, every time I run a sample of a patient for the hemoglobin value may not always come the same. For example, if I said 14 was the point which I was looking for, I may get 13.8, I may get 14.2. So that means I am not always going to get it certainly at the same point every time. This is the simplest way to explain the whole thing, because the idea is that at every given point the values are going to be slightly different than where we stand. So this part of it is what is called uncertainty of measurement. You will never be able to get exact values all the time. So what are you trying to do by putting a quality control, whether you're putting the internal quality control or using the external quality control, quality assurance material? You are trying to reduce this uncertainty to the lowest possible value. For example, Dr. Mani also just told you about the CV values of hemoglobin. He said that majority of the times in hemoglobin, the CV values or the variability of the thing between the various runs will be less than 2%. So you will not have a huge variability of the value. But come on, let's now look at it. Now look at a parameter which is, for example, platelet count. When you have a variable which is at a lower levels, the variability between the counts every time will be higher, right? So this is what is, in short, or in summary, what is called the measurement of uncertainty. You want to make sure that the uncertainty with respect to the measurement is as minimal as possible. That will make you as accurate as you can be with respect to a patient's any parameter of the patient's profile that is done. I hope that answers a question to an extent.
Yes, sir. Thank you, sir.
Only thing I would like to add is actual very definition of measurement of uncertainty involves taking uncertainty into the entire process, even like the sample storage, sample transportation uncertainty. All those uncertainties have to be put into a mathematical figure and measure the uncertainty, which is practically impossible to do. So for all practical purposes, most laboratories, the measurement of uncertainty ends up being the coefficient of variation.
Yeah, the analytical part of it.
Analytical part of it.
Thank you, sir. The next question is, what are the important steps that we do in lab before and after running the sample every day?
Okay, so before you get the sample into the laboratory, the most important aspect is, have you, if there is a requirement for, say, instance, fasting, have you ensured that the patient was fasting? So the pre-analytical variables which are going to be affecting a test is what you need to make sure that this before the sample is collected. Now, after the sample has been collected, the sample needs to be transported in a certain way to the laboratory. For example, if there is a sample which cannot be put with ice, we should not put it with ice, right? For example, if there is a sample which cannot be transported at the ambient temperature and has to be transported at 2 to 8 degrees, then we should transport it at 2 to 8 degrees. Or if there is a sample which needs to be transported on dry ice because it needs to be frozen, then we need to transport it on dry ice. So this is the transport part of it. And once it's been received in the laboratory, the integrity of the sample again needs to be checked by the laboratory to see whether the sample was reaching the laboratory in the way they had expected it to reach them. Once that's done, the pre part of it, for example, if you're doing a hemostasis testing, you might need to do centrifugation at a certain speed, etc. So you'll do centrifugation of the sample, and then you will ensure that the sample is put across in a particular analyzer if you're using an analyzer. Mind you, like there are certain conditions wherein the centrifugation also might be need to be done more than once. For example, when you're testing for lupus anticoagulant, you want to have absolutely platelet poor plasma. So in such circumstances, double centrifugation. And I'm not going to touch the analytical part of it. I'm assuming that the analytical part is any of the test which is done. So once the test has been performed, nothing is complete unless the paperwork has been done. So the entire paperwork with respect to it, whether it comes to ensuring that the quality assurance paperwork has been done or the report has been transcribed in the appropriate manner and interpreted in the right possible perspective, and the entire detail has been put on the report, again, the process is not complete. Not to forget the final part, which is ensuring that the sample which has been tested needs to be stored in an appropriate manner. So post sending the results out of the patient, you would still want to store the sample for a stipulated period of time, either because of regulation or because of retesting or add-on testing which you might need to do on that sample. Otherwise, you would need to bleed the patient again. And all this activity, right from the pre-analytical to the post-analytical part of it, should be possible to be audited at some point of time in case we want to, and at the same time documented in an appropriate manner.
Thank you, sir. I hope that answers the question. And the next question is, how do we recalibrate the controls?
Recalibrate the controls. Okay, so you don't recalibrate the controls. Control has a specific defined range, and calibrator is a separate entity. I did touch upon this in large detail during my talk. Calibrator, as I told you, has got a defined value. It's got a target value. So every time you use a calibrator, you are expected to get that target value. And if you're not able to get that target value and you have a huge variability in your values, then that means there is something wrong with your instrument and it needs to be looked at in an appropriate manner. So first thing, calibrator, again, every time any material is used as a calibrator, it will have a traceability to a reference standard, right? So I had asked, in fact, one of the quiz questions where I asked in the CBC parameters, which one is, which parameter actually has a calibrator. So there is a reference standard only for hemoglobin in a CBC. You don't have a reference standard for any other parameter in the CBC. Everything else has what is called a reference methodology and not a calibrator. Now coming to the control part of it, the control will always have a range which has been defined by the manufacturer. When you run a control in the instrument, the manufacturer's values on the manufacturer defined values, you may not be able to achieve them in your instrument. And that is where you will need to what is called redefine the range of that particular control material that you're using. You actually define your own mean after running the control sample for a specific number of runs. Ideal number of runs is 20. It is difficult to do it in a usual hematology control, but people invariably run it in parallel. A lot of us, for example, we actually run 5 times with the previous one, make that as our mean, and then decide our the standard deviations across it and put it across in the analyzer and follow it up on that. So you actually define the mean in your laboratory and you define the range of the control in your laboratory, and then basis that you go ahead and look at the values. Now in a hematology laboratory, when you're doing it for a CBC value, it is always a challenge to handle it, because every time the life of the controls that you get is stipulated for a certain specific amount of number of days, and overlapping will obviously make it very expensive for you to run. So one has to find a way to ensure that you are able to get consistent results, and yet you are able to make sure that you are able to get your lab mean. I hope that answers the question.
Thank you, sir. Sir, Mani sir, would you like to add anything?
In the sense that the control is not meant as a calibrator, but what you have to do using the controls is, for every analyzer, you have to measure the highest CV. So that CV tells you that this is the way where my analyzer's error lies in. A new analyzer will have a very tighter CV. An older, if the CV keeps on increasing, then it means that the analyzer maintenance is not good. So it requires, so the CV has to be also monitored. So you have to use methods to reduce the CV, and the CV is based on from the CV. Say if it is something is 4%, you can use the mean value of the control given to define your plus minus 2 standard deviation using the CV. So if a mean is say given as 10 grams hemoglobin in the control, then you can use, if it is a 4% CV, then you can use plus minus 3 ST will be 1.2. So it will go between 10 minus 1.2 and 10 plus 1.2. So that is the way it will be used uh, for the 4% variation.
Thank you, sir. While we are on the topic of calibrator, there is a question that can we use the calibrator as control in a situation where we are out of control and yet to receive the new lot?
Well, if you use calibrator as a control, then you have to be, somebody like Elon Musk or somebody, because that is the only person who can keep on affording a calibrator as a control, because calibrators are very expensive and they have a specific traceability. While it is not wrong to use it, but at the same time, it may not be really right to use it. So calibrator, as I told you, has a target value. It does not really have a range, though a lot of companies actually come to you and tell you that, I'm getting the value in the range. That's not really true. It has a defined value. Calibrator always has a defined value and it's for controls. On the other hand, are used for precision and they are used for understanding whether your systems are functioning appropriately, and so you give them a little bit of a leeway. You allow them to work in a two standard deviation range. So controls are always relatively much cheaper than calibrator, and therefore control should be used as a control, calibrator should be used as a calibrator, and I would prefer not to overlap it. Dr. Mani, you want to add anything? Please go ahead.
Yeah. So a calibrator, there are certain tests in which you don't use control, you use only calibrator. For example, your pH meter, you will be always calibrating before you run a pH. So in that there is no control, it is a calibrator. The second place where something acts really as a calibrator is the some of the flow cytometry beads, not all of them. Some of them act as a calibrator, but as in general, since the calibrators have an assigned fixed value, they are always very difficult to manufacture and more expensive. So generally, calibrators are not used as controls. The purpose we are using control is to reduce cost. Ideally, we should be using calibrator, but if calibrators are expensive, then the better way is to calibrate intermittently and use controls in between to reduce your cost.
Thank you, sir. I think that clarifies the doubt here. And another question is, what is the standard protocol for the frequency in performing calibration and quality control for the machine? Or what is the minimum frequency for performing one?
So when you do calibration in let's talk about hematology analyzer here. So there are two types of calibrations which people generally do. One, when we are talking about parameter calibration, which is usually an activity which is done on chemistry analyzers, it is parameter wise calibration. The other one is what is called an instrument calibration, where you do not do parameter wise calibration. For example, what happens in a CBC analyzer, you do an instrument calibration. When you do instrument calibration, the idea is that at the time of installation, you obviously would need to do a calibration. You install the machine today, you need to do a calibration today so that you are able to know whether you're getting the desired or the results that you were expecting to get. Now you have run the machine and you want to now see when do you want to run a calibrator again. Whenever your proficiency testing tells you that you've got a significant bias, whether positive or negative, you're expected to redo your calibration, clean the entire instrument and maybe redo the calibration if there is a significant bias. Other than that, if there is no preventive maintenance in between and you do a preventive maintenance at say 6 months interval, then you will do a calibration at 6 months interval. Otherwise, if you happen to do a major preventive maintenance before that, then the calibration will have to be done before that. If we go by the accrediting body requirements, that is NABL requirements today, the calibration of hematology analyzers is recommended to be done at least once a year. That's what they recommend. But if you do a preventive maintenance at 6 months, then you are supposed to follow the preventive maintenance with a calibration. So, so if I put it in a nutshell, at least 6 monthly. And if you have a major instrument breakdown and an overall of an instrument, then after that as well. And of course, at the time of installation. Dr. Mani, anything else you want to add?
Only 2-3 things about the process of calibration. So calibration, many a times in an hematology analyzer, they don't change the calibration factor. So they run the calibrator. If the calibrator value is within that narrow expected value, then they don't change the calibration. What people have to understand is each time they change the calibration factor, again the calibrator has to be run again just to verify that when you run again after the changing of the calibration factor, the calibrator gives you the exact value. So the calibration, when you say the word, technically it means the change or adjustment of calibration factor. When you don't do the adjustment of calibration factor, you're not calibrating, you're just verifying that it is calibrated. The instrument is calibrated.
Thank you, sir. Just to follow up on that, if the calibrator is expired, can it be used still?
No, generally not.
Yes, sir.
Because expiry says that the value of the calibrator, if it might change because of the expiry, it's an unstable calibrator, so it's not going to be a reproducible value.
Yes, sir. The next question is, why do we use 3 QC parameters like normal, low, abnormal, high, normal?
So I
And
thought I touched upon this during my presentation, but nevertheless, the point is you are basically trying to test all the three levels because you're actually your clinical decisions are based on all the three levels. For example, if your hemoglobin is low, your action point is transfusion. If your platelets are low, again your point might be transfusion of platelets. Similarly, white cell counts are low. It might actually lead to a state where you might even want to give a granulocytic transfusions or GCSF therapy, right? So at lower levels also you're doing something. Similarly, when you go to the higher values, for example, you have a hemoglobin of 20 grams, or you have a platelets which are like, at the 15 lakhs or 20 lakhs, or you have a white cell count which is extremely high, you might want to do leukapheresis or platelet cytopheresis, or you might even want to do, therapeutic phlebotomies in patients of polycythemia rubra vera. So you have the entire gamut, the entire spectrum in which you are going to have clinical decisions. So when you run controls, you are wanting to be sure, are you getting the low values which are true? Are you getting the high values which are true? And are you getting the normal values which are true? So therefore, you will need to run the controls based on your clinical decision requirements. Now, for example, when you talk about prothrombin time or an activated thromboplastin, activated partial thromboplastin time. Now, in them, though there are times when you would really worry about a shortened PT or a shortened APTT, but generally when you run controls, what do you run for them? Your clinical decision point is basis elevated PT or an elevated APTT. So what do you run? You run only two levels. You run a normal level and you run a high level. Of course, there also people try to run a normal level, a slightly abnormal level, and a very high abnormal level. But that's again a decision which has to be taken by the laboratory, keeping in mind what is their practice. For example, in cardiovascular or in neurological centers, you would want to do that definitely. But in others, it may not be really necessary. So again, as I pointed out during my talk also, clinical decision point is what defines as to how many levels of QC should be run. And more importantly, in the context of Six Sigma today, a lot of times you might want to reevaluate whether you really want to run so many QCs or not, depending upon how is your sigma matrix of the laboratory. Though we didn't touch upon that, and again, probably for this talk, it would be too much to talk about in terms of sigma metrics. But if your sigma matrix is high, your number of QC requirements might eventually be much lower than what you actually do. Dr. Mani, anything else you would like to add?
Uh, in the sense that it is basically, as Anil has said, is one is a clinical decision. The other portion is also laboratory decision, especially where you are converting a quantitative to qualitative, like immunoassays. Then a close to cutoff uh, control is what is very important, because cutoff is a portion where you want to know how much of variation it is going to be there. So for example, if you're doing an HIV and something comes close to cutoff in your ELISA, you want to know whether you have to keep the patient positive or negative. So in those issues, those cutoff values and the decision making values are very important, and that is the reason why the number of controls vary between various tests and what is done. So in a coagulation, you might want one at the point where you are going to say whether it is normal or high, and one at the point, especially in PT, between 2 and 3, where you are going to use for decision on anticoagulation.
Yes, sir. Thank you, sir. I think that answers everyone's question here. The next question is, could you touch upon MCV lab mean, as it keeps trending as control ages, even if it is within the expiry period? I think this might be specific to certain lots. The question is for
So
both
I
of
think that is where the point of contention is with respect to using a 10x rule in certain parameters of CBC. You know, in fact, there are a lot of people who would not advocate using a 10x rule at all, or even 8x rule at all, for deciding whether you wanted to do anything in that particular case. Now, generally speaking, the point is valid. When you, as the control will age towards the end of the, the open vial stability, the MCV will have a relative trend towards a higher side. So, genuinely speaking, I think the laboratory, and again, the coefficient of variation in MCV then becomes much higher. Having said that, we may or may not apply. I don't really have a very direct answer on this. The simplest way to look at it is, are you really finding a huge variation between what you were seeing yesterday versus today? Then I would just like to change my control, at least the open vial part of it, and take the next control and run it and ensure that my values do not really markedly change. Other than that, it is difficult to really do much about it, because perhaps it's because of that reasons only that 10x rule becomes a challenge in hematology.
Yeah, yeah. Only thing I can add is that in my experience at least, the CBC values which show a huge amount of drift is actually MCV, and I think it has something to do with the dust accumulation. After a service, it will come back down, and slowly it will start trending up to higher or lower side based on the dust environment in the lab. So only thing is, if it is having too many shifts are there, that shift is to be used by the lab to decide how frequently you want to have your preventive maintenance of the analyzer. So if there is too much shift happening, then get a more frequent preventive maintenance, because the lab environment might be, in India it is very difficult to make it a fully dust proof area. We are in many parts, so that adds up to the problem.
So the follow-up question here is, if hematology lab mean is plus or minus 3 SD and coagulation lab mean kept at plus or minus 2 SD is acceptable?
Didn't get your question. What did you say?
Sir, as a
See,
follow-up,
basically the person has asked, why are we using plus or minus 2 SD and plus or minus 3 SD? So ideally plus or minus 2 SD is, if you want too many false calls, you end up taking plus or minus 2 SD, so that you are never out of range. But if you are a person who wants the call only to be genuine and not a false call, then you use plus or minus 3 SD. As Anil has said in his talk, that 5% of values will normally fall outside plus or minus 2 SD, even if the analyzer is stable. So 1 in every 1 in 20 values can fall outside plus minus 2 SD. So that means that using plus minus 2 SD will give you too many false calls, that there is an outlier. So that is why generally it is used as a warning plus minus 2 SD. Plus minus 3 SD is what is used as actionable limit.
thank you, sir. Sir, Anil, sir, you have anything to add to this?
No, I think we have covered most of the stuff. The only important aspect is, please remember that when you are trying to get QC material uh, in hematology practice, especially when you're talking about the CBC for that matter, it is a challenge to ensure that your QC material is stable. That's first, and you are able to get the lots every time you finish your lot. So making sure that you have an alternate mechanism of handling QC material, what I touched upon in my presentation as a retained sample testing, is something which I would surely recommend to everybody, to make sure, because you can't just start retained sample on that day. You should have defined your reference interval for your retained sample testing, and that you should have done over a period of time. So as a usual practice, it is not something which is recommended, but if we are able to make sure that we have generated some data over time on it, it'll be easier for us to use it as a contingency plan when we do not have a QC material available. So, and that happens in real practice. Even the best of the centers getting QC material sometimes can be a challenge. We've seen that happening in COVID as well. Sometimes we were not able to get the QC material appropriately. The other important aspect is, as I mentioned about calibration previously, we must ensure that when we do a calibration on the hematology analyzer, we are expected to run the calibrator at least ideally 10 times. And invariably, what you would notice is your company people who you have a agreement with, they generally want to run it only 5 times and use the same calibrator in 2 or 3 centers and stuff like that. So look at it, because then obviously you're running it only 5 times and then you don't have the reproducibility data available with you. So therefore, look at that as well as a part of your activity. And finally, I did mention about what I told you already. That's when you're talking about calibrator, the calibrator is only there. Actually, it's only a standard. The standard is only available for hemoglobin. All the other parameters in a calibrator which they are providing you, they are actually giving you certain values which they have found using reference methods. So whatever reference methods have been used, they are not actually giving you a calibrator which is like the calibrator. It is not traceable to the calibration material. It is actually traceable to the reference method. So that's also something which you need to remember. As far as the coagulation tests are concerned, there you have calibrators. Not in all of them, in some of them. Dr. Mani did talk about D-dimer, and we don't have a calibrator in D-dimer which is traceable to all of them as a uniform activity, and that's why we have that variability. And last but not the least, do we have a mechanism of handling control costs? Because there are a lot of people who talk about controls as a cost also. As far as the cost of the control is concerned, for a hematology analyzer, generally you use a QC material from the companies directly. Of course, that possibly might change in due course of time because people are now looking at having third-party controls. Anyway, we will walk the bridge when it comes. But most important is coagulation. You can still prepare your own quality control material, at least for the normal controls. So normal pooled plasma, which is used by a lot of people in their centers, as long as you're able to define, because in any case you're going to be defining your mean and reference range for pre-T and APTT. So it's not a bad practice to have a normal control from the plasma which you have prepared yourself. Of course, the biggest challenge which you will face in that also is what is the stability. So as long as you keep on testing it, you're getting consistent results. That's a reasonably good way of reducing your controls. I hope I covered a lot of stuff which was important. Sindhura, and is there anything else that you would like me to touch upon?
Yes, sir. A question is there on how to generate, read, and interpret Bull's algorithm, moving averages, and use of daily names.
Okay,
You did
so
touch upon it.
so I did talk about it a little bit in one of my slides where I said that there is something called moving averages. What happens is when you run your samples in the machine, there is a certain values which keep getting generated at a certain way. Nowadays, when you talk about moving averages and Bull's algorithm, you can use that in the defined softwares which are available. For example, Unity software or softwares like that, where the data is coming in from the machines directly from all the samples. And then basis a certain trend, you are able to define, are you getting all your values, in a certain manner or not? And wherever there is a drift or a shift, the software is actually able to alarm you. And basis that, you are able to take appropriate actions. Now, it's not a bad idea to use this, but it is not really recommended to be used as an alternative to the usual QC material. You use this is the patient data which is used at certain levels, say for instance, the low level or the normal level or the high level. You keep tracing the patient data and see, are you getting that data in that same sequence or not? And basis that, you're able to get that. So there are statistics which are involved. And of course, when you look into that, the data gives you an insight that there is no bias, or even if there is a bias, what kind of a bias are you dealing with? Anything
Just
else you would? Yeah.
yeah, I would just regarding Bull's algorithm, 2 points I would like to add. One is there are reference values for Bull's algorithm which are having an assumption of a general hospital population. General hospital means which takes all kinds of patients of all specialities. The second assumption of Bull's algorithm is that your patient population is constant. Suddenly, if you add suddenly where there is no oncology, when you add oncology, your Bull's algorithm will go haywire because your patient population has changed. So these two things have to be kept in mind. So the generally defined reference value for Bull's algorithm generally doesn't work. I work in an oncology, purely oncology center. Those reference values don't work. But Bull's algorithm doesn't have what is called as a very good calibrator value, but it has a very good reproducibility value if your patient population is constant. So that is one assumption which you have to which is underlying the Bull's algorithm rule. So whenever there is a change in Bull's algorithm, you have to think whether something in your hospital or patient population has there been which major change. Otherwise, the Bull's algorithm will work fine.
Yeah, so generally the trend for majority of the hospitals like ours is when we are trying to target Bull's algorithm, we are only targeting patients which are coming from health checkup. So do not try and target patients from every section. The moment you're going to target patients from every section, you are in trouble. And fortunately now what happens in current softwares, you are able to actually define from where the samples are coming in and then look at the moving averages. But as Dr. Mani mentioned, yes, it is not easy to, just follow it blindly.
Right, sir. Thank you. Sir, there is one last question. Can you give an example of calculating the measurement of uncertainty, say, for example, for hemoglobin? I think there has been some doubts about the measurement of uncertainty for quite a few people.
Okay, so when I was showing my presentation, in that I showed you how to calculate a CV. Now, if you are only looking at measurement of uncertainty, then it is CV multiplied by 1.96, and that's what will give you the measurement of uncertainty in terms of numerical data. But what are you basically trying to do? You are trying to figure out how much variability are you having from what you were expecting that value to come in as. For example, if you take a control sample, I told you control sample has got a range, but you defined a mean for your laboratory. Say for instance, for a normal hemoglobin, you had defined a mean of say 14. Say for instance, when you run this sample, you're not getting 14. You will never get 14. You will maybe get 13.5 or you will get maybe 14.5. I hope you understand. So now every time you run this sample, there will be some degree of variability from your target value which you are expecting, the mean value which you are expecting. Now this variability cannot be huge. So if you defined your range to be between whatever we discussed with respect to 2SD, it has to be, say for instance, my 2SD for example for this hemoglobin was 14 plus minus say 1.5. I'm just giving a vague example. So if my values go beyond 1.5 on either side, or positive or a negative, that means my variability is much beyond what I had expected it to be. So as minimal a variability as it is, that makes the test more robust, more reproducible, and more reliable. The higher the CV and the measurement of uncertainty, the more unreliable is the test. For example, if you look at ELISAs, the acceptable variability is almost about 15%. Whereas when you talk about a test like hemoglobin, the variability of more than 2% itself is a big variability. Or for that matter, if you go to tests like potassium, the window itself is so narrow, 3.5 to 5.5. So if you have a variability of say 10% there, it's huge. I hope you're getting my point, what I'm trying to say. So idea is that we do not want the variability between the values to be so high that it's going to be affecting the patient care. So measurement of uncertainty in terms of calculation, as I told you, is measured by doing the way I told you, the standard deviation and CV, and then in a simplest way, multiply it by 1.96. But if I go across on a typical measurement of uncertainty way, the way it is actually done, it has to be a proper separate 1 day seminar.
Correct. So the plus minus 2 times CV percentage is what you can use for daily calculation. So if CV percentage is 4, and if your measured value is say 10.8 plus minus 4% of 10.8 is what is where your true value of the patient is going to be. So this actually is useful clinically when you are having borderline values to decide whether you want to intervene or not. That's the only way it is done.
Thank you, sir. I think most of the questions have been answered by both Anil sir and Mani sir here. There are a few smaller points which have already been covered during the presentation by Anil sir, and also highlighted in the discussion, in the summary discussion by Dr. Mani sir. Now, Gujral sir is online here. Sir, would you like to add anything?
No, nothing. Thank you, Anil and Mani. Both of you made it so interesting and simple. I joined late though, but I think there's so much you can talk, and there's so much ignorance and about and scare. Like when you started your talk, you mentioned examination point of view, we read and we are happy not to see the question. Even if you cram it, we don't know how to answer it. But I think you guys have cleared so many doubts and given a direction to students how to think about quality assurance program in a hematology lab. Thank you very much, both of you.
Thank you, sir. Thank you very much, sir. Thank you, Dr. Mani, and thank you, Dr. Sindura, also.